the statistician's on crack. That if you understand one thing and one thing only from statistics classes, it's how to understand a probability distribution and how to analyze it like this. Because this governs how much you guys pay for car insurance. What you're doing right now, just this determines your average payment per month for any insurance policy you'll ever hold in your life. Car, life, auto, car, life, health. This is determining. I actually have, next week we'll do an example in class, an in-class quiz where you actually play actuary. You figure out how much you have to charge for a premium to make sure your company makes enough money to pay off the claims. And it's all based on this. It's totally rad. Totally rad. But it starts with dice. It starts with dice. I didn't mean to freak you out. You guys got really quiet there all of a sudden. I didn't mean to freak you out. Just trying to show you that the power is power in this tool. All right, grab your TIs. Let's get them ready. You see that okay-ish? I'll zoom in a little bit. Yes, there is a formula, but I'm not going to. I'll show it to you later. No reason to memorize formulas in this class. Memorize usage. All right, so you set this up exactly the same way that you set up any other weighted average. L1, L2. In L1 goes your data. So let's go ahead, stat edit. I think I have to save some of this. Yeah, that's 105 stuff. That is 244. I can get rid of that. I'm going to go L5, L6. You guys go wherever you want to go. I'm going to try to get it focused. There we go. So L5 is 1, 2, 3, 4, 5, 6. L6 is the probabilities, 1 and 6, all the way down. TI gives you decimals. It's totally fine. To get your average and your statistics, what are you going to run? Same thing you always run. Just make sure you tell it the lists too, right? Make sure you tell it the lists too. Sean, let me know if the Casio behaves with this. Oh, should, okay. Because the old TIs would misbehave if these were less than 1. And I was hoping the Casio caught that mistake and takes that book too, so that's fantastic. Let me know if the 89 works and the Inspire works as well, Omar. All right. Okay, there's your average. 3.5. It calls it X bar. I want to come back to that book. Say that again.
There's no standard deviation.
Aaron says, what the hell? There's no standard deviation. Did anybody else notice that?
Yeah.
There's a blank right here.
Why?
Why? Kayla screams. It was a quiet scream. It was a good scream. I want to know why too. Omar said it's undefined. You guys says undefined? That was clever. Very clever. Why? Why is it not? Is there seriously no standard deviation of this data? That's crap. There's got to be a standard deviation. The data's not. The only way that there would be, well, actually, if it was a 0 standard deviation, that would mean all the data was exactly the same, and that could be 0. But it's saying it's undefined. It's not even there. That's crap. But what is? Do you remember what S stands for? Which standard deviation? The sample standard deviation. So what it's saying is there's no sample standard deviation. What's interesting about that is that's perfectly logical for 2 reasons. I'm going to give you the first one, the intuitive one first. You didn't enter a sample into your TI right now. You entered the population parameters, didn't you? When you roll a die, 1/6 of the time you get a 1. That's not the sample, that's what happens all the time. 1/6 of the time you get a 2. 1/6 of the time you get a 3. 1/6 of the time you get a 4. There shouldn't be a sample standard deviation. It's not a sample. It's the population parameters. That's kind of slick, huh? So then I asked the question, well, where's the population standard deviation? It's that guy. Little sigma. We mentioned him a few times in passing back in the day, and what did I tell you? I said ignore him for now. He'll make more sense later. And guess where we are? Later. We are later. Now we need to talk about it because now you actually do have a population. You've put in the population behavior, the behavior of the population of a single die. So your standard deviation, who said it was a 2? That's a damn good guess. It's 1.7. Damn good guess. 1.7. It's a tough one to estimate because it's not a bell-shaped curve. When they're bell-shaped curves, they're much easier to estimate. We'll get a few of those next week. We'll get some skewed ones next week too. Now, here's a problem though. Is anybody else wrestling with why that's being called X bar? Or have you already been thinking about lunch because it's getting close to 12? Probably. So what is X bar? Right, which average in particular? That symbol stands for the sample average, right? So now we got, what the hell's the population average? Where is the population average? The answer is the TI will never call it by its correct name. So you have to know, when you've entered a population into your TI, you don't call that guy X bar, you call him U. You call him, okay, let's fix him right now before we get out of here. You just have to know this, the TI is not smart enough to do it for you. Okay. So when your TI comes back with these parameters, because that's what they are now, is parameters, there's your population standard deviation, 1.7. Nice, Tony. Your population average, 3.5, should be called the lowercase Greek letter mu. I know I've mentioned him before, but only in passing. And the reason was, it wasn't important to talk about before now. Little sigma, little mu. Those are our parameter values. When you have an entire population's behavior, you call them little sigma for the variation and little mu. They still behave the same. They still behave the same. To quote Sarah's awesome analogy from last time, mu is still where you put your finger to balance the cookies. Imagine a tray with 6 types of cookie on it, all of which are equally weighted. The 1 type, the 2 type, the 3 type, the 4 type, the 5 type, and the 6 type. Imagine what that tray would look like if they're all equally weighted. Equal stacks for all 6 types, right? Think about where you have to put your, let's make it quick. Hang on. It does, doesn't it? Hang on a second, I'm going to grab this thing real quick for you. No, let's turn it on. All right.
3 bars on one side, 3 bars on
Sorry. Yes, exactly right. I got the thing set up wrong. Hang on one second. L5, L6. Okay. All right, gotta fix this a little bit. Hang on one second there, friends. 1 to 6. All right, I'm gonna go 1 to 7. That's right. All right. Here's your 1 cookie, 2 cookie, 3 cookie, 4 cookie, 5 cookie, 6 cookie. Where would you put your finger to balance that? Right there at 3.5, right? 3 bars on 1, 3 bars on, to balance it right there in the middle, 3.5. The plus or minus is trickier. That 1.7 is a little harder to see because you'd have to add up these distances, and those distances, average them all out. But 2.5, those were fantastic guesses. Very, very close what they truly were. Fair enough? That's the idea. That's the idea. I did that graph very quickly because we're out of time. We'll do more graphing of that on your TI next time. The TI has a bit of a hard time graphing these distributions. We'll go through it together, probably. Not important right now, anyway. Cool? We're going to stay in this topic, well, 4 more weeks. Sean! Oh, we'll get you in a second. We'll fit. Fair enough, friends? Have a great weekend. Sorry, but we didn't get to the second dice. Yeah, if you don't mind, just bring the dice back up, drop them off on the way. We'll grab 2 dice next time. We ran out of time before we got that. That's totally fine. I love where the discussion went today. Rock on, my friends.